remember yesterday? What was yesterday? We learned about definite integrals. Why, do we ask? What are we actually finding when we are finding definite integrals? Well, let me just check that you've been paying attention at all, ever. What are we finding when we find the derivative of a function? Yes. Ali said gradient. Okay, so when we differentiate a function, we're finding an expression for the gradient. Excellent. When we integrate something, we are finding the area underneath the curve.
We are? I didn't know that.
Well, that's what I haven't told you that. I'm just telling you that right now.
No.
So that means that if I was finding the integral of this expression here between the values of 1 and 0, we are finding this area here. Okay? So it's the area between the curve, the boundaries that they've given you, and the x-axis. Okay? So that's what definite integrals are doing. Lovely talking. Yeah. Okay? Good? So, some more examples. So we did this yesterday. So this will be good for Shelby because she can catch up. So, just now. Hit me with it.
Okay, so 3x cubed over 3 plus 2x.
Then what do we do?
Then we have to put our bracket.
Yeah, so we put a square bracket. Yeah.
Square bracket, then we put our 1 and 0 on the right hand side.
Nice.
And now we substitute. So
let's look, see if we can substitute.
First we cancel out the 3 and the 3. Okay. Now we're left with x cubed plus 2x. With our bracket and our numbers. So now we substitute those numbers into our equation. So it's 1 cubed plus 2 times 1 and minus 0 cubed plus 0. So that gives us 1 plus 2, which equals 3. Okay, minus 0. 3 minus 0.
Yep.
3, yeah.
Ali, why don't we need to write plus c here? So do you remember, normally when we integrate, we would write x cubed plus 2x plus c. Why do we not need to do that? Remember? Can anyone help? Why do you think you don't need to get cancelled? It does get cancelled out because remember, yeah, because it's a constant. We would have that constant here, and then we'd be subtracting that constant from here. Yeah, does that make sense? So if we had the constant here, we would have plus c, and then we'd be taking away the c from here. So there's no point having it. There's no need to have it. Okay. So just checking because sometimes people will start saying, "Yeah, you said we don't have plus c," but these ones you don't. Okay. And remember, it's always a numerical answer. So here they've asked us in words. Find the area described. The area between the curve y equals x squared, the x-axis, and the line x equals 1 and x equals 3. Now I would suggest that you perhaps want to sketch a little diagram of what's going on. Oh, that's not good. Okay, so there is my y equals x squared graph. You will be happy with that? Yeah, totally. Oh, it is great. Let me do it. Okay, you're all happy you would draw that as x squared, yes? And we would then have the lines x equals 1 and x equals 3. So here's where x is 1, and here's where x is 3. So they want us to find this area here. And now we need to actually establish, well, how would I write that?
3 minus 1.
I need some more, I need to explain. So these are the words. This is my diagram. How would I write it here? The integral sign, yeah. Secretly, what you notice about all the numbers all the time? Which one goes on top?
The big one. 3 over 1.
Yes, so the big one goes on top. Where am I? Here? Okay, so I would have 3, 1. Yeah.
And
The function. Yes.
yeah.
And then dx because we're telling ourselves to integrate. Alright? So from those words, that's what we've been asked to do. You comfortable with that, Lydia?
Let's do a lovely example. Why don't we multiply the power by the number before the x when we reverse it?
We're different. Remember we're integrating. Yes, stop. No, so our power increases and we divide by a new power.
Okay, so right now number 2 bigger number 0.
Alright, so we're all comfortable with it. From these words, we would write this question. Yeah? So now let's do it. Skyler, do you want to do it?
X, 3x third,
So,
3.
is there any number here now?
No.
So remember, integration, hold your horses, Kelly. Integration, add 1 to the power, divide by the new power.
X3, number
Is there a reason that we're doing like this? And then we hang on bracket. We hang on numbers at the end of our bracket.
We do not do
Do
we not do plus x?
No, because there is no number there. If it said plus 5, then you would have plus 5x. Yes? Right, okay, now what do we do?
Oh, with the number.
I didn't do that. Put the numbers in, yeah. So 3 cubed over 3, subtract 1 cubed over 3. So 3 cubed means 3 times 3 times 3, yeah? And then divide by 3. And then 1 cubed is 1. And so that's subtract 1/3. Yeah, you remember that? Yeah, but you're subtracting. 6. What?
No, you change.
Alright, so we've established that 9 whole ones, subtract 1/3 would be 8 and 2/3. And if you wanted to, you could change this to an improper fraction. So if we remember, we need a denominator of the same. So at the moment it's a 1, and we would need a denominator of 3. So we multiply both top and bottom by 3. So that would be 27 over 3, subtract 1 over 3, which is 26 over 3. And then how many times does 3 go into 26? 8 times, and then there's 2 left over. So you get the same answer either way. Okay? Okay, now, this is where it starts to get a little bit trickier, in that in some cases, part or all of the curve is going to be below the x-axis. Okay? This diagram here is a good display of that. So, if you were to find the integral of this function here between the values of 2 and 0, okay, which is what this question is asking you to do, you would end up with a negative value. Okay? Should we do it to show you that it's true?
I really
We will. All right. Olivia, can you integrate this bad boy for me, please?
X cubed over 3 minus 3x.
Oh, to the 2. Over 2. Nice. So we've got x cubed over 3, subtract, and obviously our 2's cancel here. And then we chuck our values in. So we've got 2 cubed over 3, subtract 2 squared. Take away 0 cubed over 3, subtract 0 squared. So 2 cubed is 8. Yes, 8. Over 3, subtract 4. Take away nothing. Nothing. So you've got 8/3, take away 4. Now here we probably do need to make sure we've got them as the same denominator, because it's not as easy to identify what value we've got. So at the moment, as I said, here you've got a denominator of 1. So to make them the same denominator, we have to multiply both top and bottom by 3. So then we've got 8/3 subtract 12/3. So 8/3 subtract 12/3 is obviously negative 4/3. And lo and behold, it's a negative value.
So we leave it as the improper fraction?
Yes, you can do. If they've asked, now at this point we need to check what they're asking. If they're asking for the actual area, we would then say it is 4/3. Okay, because the area itself is 4/3. The fact that it's negative just tells us it's below the x-axis. You all comfortable with that?
Mm-hmm.
Yeah? Yes. Now, the issue arises, so that in itself is not tricky, it's just the fact it was underneath the axis, it's 0. The problem comes on here in questions like this. Because if I've got this same function, and I'm now saying I want the interval between 1 and -1, that means that the 1 is here, the -1 is here. If we did what we did just now, then what would happen is that this portion here, being negative, would cancel out some of our answer here. Does that make sense?
Yeah.
So it means that what we have to do is, if any of it is below the x-axis, we have to do it in 2 different sections. Okay?
So double the math.
So, well,
So that would be -1 to 0 and then 0 to 1?
yeah, essentially, it's not necessarily double math because the integration is the same because it's the same function. You're just going to have to do a bit more substitution, which in itself is not too stressful. So for here, as Trishan just said, we would actually then do the integral between 1 and 0. I'm just going to write fx because I can't bother to write that one. And then we would add on the integral between 0 and -1. So we would split it up because some of it is negative.
But you would still have to write that.
Pardon?
Okay, it's not going to write that.
Why is it tiny baby?
We're recording.
Alright, so we've just recorded this. I didn't realise. Joshua and Shelby did some good work. I'm going to take
Like you think she'll be happy that we understood the concept.
Quietly because the speaker's back there, so she can't.
So, you're all awesome. And as I said, we've got 4/3, we had a positive area, and we expected a positive area because it was above the x-axis. So this part here, we're expecting to be negative because it's below the x-axis. But it's the same thing. So we've already got our integral. We know it's going to be x cubed over 3 minus x squared. This time it's between 1 and 0. So we've got 1 cubed over 3, subtract 1 squared, subtract, divided by 0, you'll know that when we stick 0 in there. So that's 1 cubed, subtract 1. So 1 cubed, 1 cubed? It's not 1 cubed, 1/3. 1/3 subtract 1 whole 1 gives us negative
It's a negative, negative.
I mean, so you're starting with a third and you're subtracting 1.
Oh,
Negative
Negative 2 thirds.
I just said that.
Nice.
down to one.
I don't want to vegetable on it.
It's negative plus.
Alright, so we've got negative 2 thirds. So if we want to find the total area, we would ignore this negative sign. So we would say that it was, so we've got 4 thirds plus 2 thirds. You're happy with that? So the total area would be that area A, which was 4 thirds, and then we would add on area B, which in itself is actually 2 thirds, so we've ignored the sign of it. They've got the same denominator, so we just add on numerators. So that's 6 thirds, 2, which is 2. Sorry, Chef?
So why do we ignore the sign?
Because the only thing that the negative does is tell us it's underneath the x-axis, and that was the whole reason for us doing it 2 separate bits. Because if we'd done it in one whole one, we would have had an answer not enough. Okay, are we good with that? So, summary. Area is always positive. Definite integral is positive areas above the axis, negative below. We need to know whether it crosses the x-axis. Blah blah blah. Blah blah blah.
We have an extra page.
Oh yeah, that's for a little bit in a minute.
No, we're